Hello and welcome everyone. And now we are seeing the analysis of doubly reinforced beam. So we have discussed in which case we have to go for doubly reinforced beam. And it was the case when the ultimate moment of resistance due to the external loading exceeds the limiting moment of resistance. So in that case, we do not design a singly reinforced beam because that would become an over reinforced beam, which is prohibited as per the IS code. So we go for doubly reinforced beam, and this is the figure of doubly reinforced section. And here we have assumed that we are going to design it for ultimate moment of resistance equal to 400 kilonewton meter. Now we have provided reinforcement steel in compression zone whose area is ASC, as well as in tension zone also whose area is AST. Now I have broken this image into two simple parts, and we are trying to understand this by superimposing one over the other. Now this is the figure 1 and this is the figure 2. So in these two figures we have shown two sections in such a way that the figure 1 represents a singly reinforced beam section, and this is a balance section which is going to resist the load of mu limiting of the section, which is equal to 350 kilonewton meter. Okay, so this is a balance section, and in this case mu is equal to mu limiting. Okay, and we have provided steel at the bottom, but we have also provided few holes at the top, which has been discussed to you. Why this is left? Just to accommodate these compressive steel bars. Okay, now in figure 1, compressive force is C1 and tensile force is T1, and by equilibrium of forces C1 is equal to T1. Okay, and the value of lever arm in figure 1 is equal to D minus 0.42 XU. Okay, and with help of these parameters we can easily calculate the values of moment. Now in the figure 2 we see only steel bars. There is no concrete. I have specifically written it, there is no concrete. So there are steel in the tensile zone whose area is AST2, and there are steel in the compressive zone whose area is ASC. Now here also there will be compressive force and tensile force C2 and T2, and by equilibrium of forces C2 will be equal to T2. Now if we superimpose both the section, then we can write C is equal to C1 plus C2. Now this C is the compressive force on this section. Okay, also T is equal to T1 plus T2. Now T is the tensile force in the doubly reinforced section. Okay, and we can equate by equilibrium of forces C is equal to T. Now in case of figure 2, if you see, the value of lever arm will be D minus D dash. Now what is this D dash? D dash is the top clear cover. Okay, this is the D dash. So this is the value of lever arm, and we will be using this value of lever arm in calculation of moments in figure 2. So understanding of these figures is very important for understanding doubly reinforced section. Okay, now we have to calculate compressive force as well as tensile force on doubly reinforced section. So for that we have to calculate the individual value of C1 and C2 as well as T1 and T2. Okay, so let us calculate the value of C1 and C2. We have seen the value of C1 in case of balanced singly reinforced section is equal to 0.36 FCK BXU as per the IS code. Now why something is subtracted from this? This is because we have provided few holes. Okay, and the area of these holes will be equal to the area of these steel bars. Okay, and these steel bars area is ASC. So area of all these three holes will be also equal to ASC. And because these holes do not have concrete, so we have to reduce that much contribution of stresses due to that much area of concrete. Now area of concrete in those holes would be ASC, and this is the stress in the concrete at the level of ASC from the stress block diagram of IS code. And you have seen the stress block diagram, which is rectangular and then parabolic in the IS code also, and this value is equal to 0.446 FCK, and the level of ASC is somewhere here only in the rectangular zone only, and the stress value will be same here, 0.446 FCK. Okay, so this is very clear. So this is how we calculate the value of C1. Okay, and now comes the C2, and C2 is the compressive force in section 2, and we see in second section there is only area of steel ASC provided in the compressive zone. So we just have to multiply this area of steel with the stress in steel bars at this level, because at every level the value of stresses in steel changes because of the change in the strain diagram. This I will explain you very soon. So the compressive force C2 in figure 2 will be equal to area of steel bars in compressive zone multiplied by the stress in the steel at that level. Okay, now we add these two values of C1 and C2 to get the value of compressive force in case of doubly reinforced beam. So this is the value of compressive force C, and we have taken ASC in common here with FSC minus 0.446 FCK in bracket. Okay, so if you observe above equation carefully, you come to realize that only FSC is unknown. Okay, only FSC is unknown. Now our target is to calculate FSC, and FSC is the stress in steel in compression zone. Okay, usually steel used to be in tensile zone. Now steel is in the compression zone, so we have to calculate the stress in steel bars in compression zone also. Now we know from the stress strain curve of a steel that the behavior of steel is almost similar in tensile zone as well as compressive zone. And this is our doubly reinforced section shown here, and these are the steel provided in compressive zone, and these are the steel provided in tensile zone. Now we have also shown you the depth of neutral axis XU, and this is the top clear cover, and this is the effective depth small d. Effective depth D is always gross depth minus clear cover at the bottom. Okay, this I have also explained. Now beside this figure you also see the strain diagram of concrete. Okay, now why we have drawn the strain diagram of concrete? Because we want to calculate the strain value of concrete at this level of steel, because the steel has been embedded in concrete and there is proper development of bond between concrete and steel, so there is perfect continuity at that level. So the strain in concrete will be the strain in steel also, because they are compatible there. If they are not compatible, then there would be development of cracks. So if we have calculated the strain value of concrete at that level of a steel, so we need not to calculate the strain in steel separately. Strain in steel will be equal to the strain in concrete. And we know from the assumptions of limit state method that maximum strain that concrete can undergo is 0.0035, and here we have denoted epsilon SC is equal to strain in steel in compression zone. Now from the similar triangle we can write 0.0035 divided by xu is equal to epsilon sc divided by xu minus d dash. Now how it is written? Now we have two similar triangles. One is the larger triangle, this one, and other one is the smaller triangle like this one. Okay. Now we have taken the ratio of perpendicular to the base in both the triangle. So in larger triangle, perpendicular was equal to 0.0035 and the base was equal to xu. Similarly, in a smaller triangle, perpendicular was equal to epsilon sc and the base is equal to xu minus d dash. Now this d dash is the value of top clear cover. Okay, so this should be clear to you. From here we get the value of epsilon sc and it is equal to this value. Everything is known here. And now we can easily calculate the value of FSC, which is equal to stress in a steel in compression zone corresponding to the epsilon SC, which is the strain in a steel in compression zone. So how do we do this? This can be done by interpolation method in the graph of a stress strain curve of a steel. So in numerical problems, many a times we see these kinds of interpolation method. So if possible, we will be also doing a similar type of numerical. Now after calculating compressive force, we can also calculate the tensile force in the doubly reinforced beam. Now what is the value of tensile force? It will be simply equal to T1 plus T2 and we can directly write the value of T1 equal to 0.87 Fy multiplied by AST1 and the value of T2 will be equal to 0.87 Fy AST2. And this we can add together to get the value of 0.87 F by AST. Here AST is the area of steel reinforcement in tensile zone. And now from the equilibrium of forces we can equate the value of compressive force with the tensile force. So we have written compressive force on the left side and we have equated it with the tensile force. Now above equation will give us the actual depth of neutral axis. Now let us calculate the moment capacity of beam also. So moment capacity is calculated by multiplying the force with the lever arm and we can write from the principle of superposition mu is equal to mu1 plus mu2. And the value of mu1 and mu2 can be calculated either from the compression zone or the tensile zone. So first of all we have done from the compression zone and you see this formula here and we have just used this formula here again. Okay, and what we have done, we have multiplied the compressive forces with the corresponding lever arm. So first of all we have taken 0.36 FCK BXU here and then multiplied it with d minus 0.42 XU. Okay, so this gives you mu1 plus mu2 is what? ASC into FSC minus 0.446 FCK and this value of compressive force is multiplied by lever arm in figure 2. Okay, and this is equal to effective depth minus top clear cover. Okay, because in figure 2 there is no concrete at all, so there is only distance between the steel in the tensile zone and the steel in the compressive zone. So the distance between both the steel is d minus d dash. So we have multiplied the lever arms corresponding to the compressive forces. That's all. Now how can we calculate the individual value of AST1 and AST2? Now in most of our cases it will not be asked because figure 1 and figure 2 is drawn by us for our convenience in order to understand a complex figure by breaking it into simple figures. So figure 1 and figure 2 is drawn by us as per our convenience. But even if someone asks you how to calculate the value of AST1 and AST2, So there are very simple ways to calculate AST1, and we know AST1 is the area of steel reinforcement in tensile zone in figure 1, and figure 1 was a balanced singly reinforced beam and the moment was equal to mu limiting. I hope you remember this. And then we just have to equate the value of mu limiting with 0.87 f by AST1 multiplied by d minus 0.42 xu limiting, because this is a balanced section, and here we have used just AST1 only because this is about the figure 1. So in this equation only AST1 is unknown and we can calculate it very easily. Similarly, we can also calculate the value of AST2. We know that AST2 is the area of steel reinforcement in tensile zone in figure 2, and figure 2 was meant to carry the moment mu minus mu limiting, and we just have to equate mu minus mu limiting is equal to 0.87 f by AST2, and in this case lever arm is not equal to d minus 0.42 xu but lever arm is equal to d minus d dash. So the same thing is done here, and in this equation only AST2 is unknown and we can calculate it very easily. Now how to calculate the value of area of steel reinforcement in compressive zone? So if you see, the steel reinforcement in compressive zone is only in the second figure. So we just have to use this equilibrium equation in second figure where C2 is equal to T2 and the value of C2 is equal to ASC multiplied by FSC minus 0.446 FCK, and the value of T2 is equal to 0.87 F by AST2. So we have equated both the compressive and tensile forces in figure 2 only, and from here we can easily calculate the area of a steel reinforcement in compressive zone. So one by one we have calculated almost everything in doubly reinforced beam. So we will be discussing a small numerical on doubly reinforcement beam very soon in the upcoming videos. So till that, stay tuned and stay safe. Thank you.